Hello everyone, and welcome to today's chem lesson. Today we are going to continue our discussion about how to name ionic compounds by adding another little rule to it and introducing this idea of polyatomic ions. Polyatomic ions occur when groups of atoms come together and collectively gain or lose electrons. For example, if we look here at ammonium, this is NH4 with a plus charge. That means this nitrogen and these hydrogens, these 5 atoms together, have collectively lost 1 electron. Instead of each one losing 1, it's this clump of 5 has bonded together and then lost 1 electron. We can see the same thing down here with sulfite. This sulfur and 3 oxygens bonded together, and then after they were together, they lost 2 electrons. And so it gives these polyatomic ions a charge, and it also starts the pattern of treating them like one unit. They are clumped together, and very few things will actually take them apart from their clumps. They're located on the reference table, right, as you can see, right off of table E. This list is directly taken from our reference table. And you'll notice, besides telling you the formula, besides telling you the charge, they also give you the name of that ion on table E. And that's going to play a big part when we look at naming these polyatomic ions when they're a part of an ionic compound. They will keep their name exactly as written on table E. You're not going to do anything to their names. Last time we talked about how the ending of the negative ion gets changed to "ide." Right? Chlorine becomes chloride. Oxygen becomes oxide. That does not happen with polyatomic ions. They have a name on table E. That is the name that you will always use to refer to them by. It does not change our crisscross method all that much, but we do now need to think about these polyatomic ions. And we're going to walk through and I'll show you why our method changes just a little bit. And so let's take a look. When we have polyatomic ions, our crisscross method changes ever so slightly. Instead of just assigning 1s now, we also need to try to identify any polyatomic ions that are in these compounds. Because we learned that when you crisscross, you move the number from one element up to the corner of another, but we can't crisscross with 3 things. Right? There needs to be 2 ions, a positive and a negative, for us to do the crisscross method correctly. And so, before we move to crisscrossing, we need to say, hey, there are 3 elements in this compound. I can't crisscross with more than 2. So there must be a polyatomic ion in here. And so what happens is we need to assign 1s using table E to tell us which piece is the polyatomic ion. Is Fr2C2 a polyatomic ion? I go and I check table E, right? What piece of this comes off of table E? That's the first question we have to ask ourselves as we go to assign our ones. Because you cannot crisscross with multiple things. It's got to be just two, a positive ion and a negative ion. After you've found your polyatomic ion and put your parentheses and assigned it a 1, you're off to the races. Now we can crisscross, we can assign our charge, we can do a lot of the steps that we have already done. All right, we'll take Fr2, C2O4. We will move that 1 from the C2O4 up and over to the francium, the 2 up and over to our polyatomic ion. Then we'll come down and assign our charge, Fr1C2O4, 2. We know the first ion is always positive, second ion is always negative. Then we have to check our periodic table. But we end up with a small problem here, and that problem is that C2O4 isn't on this periodic table anywhere. C2O4 is not a thing that we can check against the periodic table. We can check francium. Right, let's zoom in a little bit and take a look at francium. Francium does have a +1, and so we can give francium a little check in our correct color. But when we go over to look for C2O4, we're not actually looking at the periodic table, we're looking at table E. And so we need to go up to table E and check for C2O4, which is here. It does have a -2 charge, so it does get a check. And now we can go on and get our name. The first ion, the positive ion, keeps its name, francium. The second ion, the negative ion, gets its name changed to "ide," unless it's a polyatomic ion, which this one is. And then we're going to take the name right off of table E. C2O4 is called oxalate, and so we're going to write oxalate right here. Now, do we need a Roman numeral here? The only time we need a Roman numeral is if there are multiple oxidation states for francium. Right, multiple oxidation states for the positive ion. So let's take a look and see if we go back to our periodic table and look at francium. Francium only has one oxidation state. It only has a +1 charge. So we do not need the Roman numeral here. And so that's our name, right? We changed a little bit. We adjusted our assigning ones, and we adjusted our checking the periodic table. Right now it's check periodic table and table E. Right now it's assign ones and find polyatomics. But the overall process has remained almost identical. We're still doing the same things in the same order. let's take a look over here at our second example. We already have numbers on each ion. The only place we need to assign a 1 would be this P inside the parentheses. But if you notice, the numbers inside the parentheses were never touched. Right, keep that in mind as we move forward, right? These 1 and this 1 and this 4 are not going to get touched. We're going to take our elements here, right? We're going to take our ions, we're going to bring them down, we're going to crisscross them, moving the 2 up and over, the 3 up and over. It's going to bring us here, where we are going to then assign our charge. First ion is always positive. Second is always negative. Then we're going to check the periodic table. Let's look at magnesium first. Does magnesium have a +2? Yes, it does. So magnesium gets a check. Then we know PO4, phosphate, is a polyatomic ion. And so we are going to find it on the table. If I can move it to the right screen, there we go. We're going to find PO4 and take a look. Here's PO4. It does have a -3 charge, so that also gets a check. And we go on to our final step, getting our name, magnesium. No Roman numeral needed because magnesium only has one possible charge. And if we come back to our reference table, right, it's +2 and only +2, so no need for the Roman numeral there. And then we take the name of this polyatomic ion, PO4 is called phosphate, and so we will write phosphate. Let's look at our third example here. Our first step is to assign our 1s and find our polyatomic ions. These need 1s. And then we need to check the reference table to find what piece of this compound is a polyatomic ion. Is it the Fe and the C together, or is it the C and the O together? Right, we could look, it would be in the same order. There's no Fe on here, but if we look, we do see CO3. That is right there. And so that's our polyatomic ion. We're going to mark it off by putting it in parentheses and including that 1. Then we're crisscrossing. We've got Fe1, C1O3 in parentheses with a 1. We're going to take that 1 from the iron and bring it up and over. The 1 from the polyatomic ion, bring it up and over. That's going to put us here, Fe1, C1O3, 1 in parentheses. First ion is always positive. Second is always negative. Now it's time to check the table. Does iron have a +1 charge? Let's take a look. Here is iron. Iron has a +2 or a +3. It does not have a +1 option. So iron, actually, we're not going to say matches the table because it doesn't. It doesn't match. It can be +2 or it can be +3. What about C103? Let's look at table E and see what table E has to say. If we find here's our carbonate, carbonate must be a -2, so it also doesn't match. Right? It does not match. It can only be a -2. Now remember, when things don't match the periodic table, if you hit this step and you're getting these don't match, we need to adjust them. We need to adjust both of these charges. We need to multiply them by the same number in order to make them match the table. In this case, carbonate only has one possible thing. I need to multiply this by 2, which means I also need to multiply my iron charge by 2. That makes my iron get a charge of +2, and my polyatomic ion, my carbonate, get a charge of -2, which means they both match the table now. So we can mark check and check and move on to getting our name. Iron is going to keep its name. CO3, we're going to check table E. CO3 is named carbonate, and so it is iron carbonate. And do we need a Roman numeral for this one? Does iron have multiple options? Iron could be +2 or +3. And since iron could be either +2 or +3, we need to specify which one it's going to be. Because it is the +2, we are going to write iron 2 carbonate. The Roman numeral always represents the charge of the positive ion. If this was a +5 and that was possible, this would be a 5. If this was a +1 and that was possible, this would be a 1. Right. This is carbonate and not oxalate because they are two different ions. Right. C2O4 is not equal to C1O3. Each polyatomic ion has a different name. Some of them are similar, but they are all different names. Now let's take a closer look at table E. Right, there are some patterns you will see on table E, right, like the presence of sulfite, sulfate. Right, this one, hypochlorite, chlorite, chlorate, perchlorate. Right, you get a lot of things that have similar names with similar formulas, right? Adding an O each time is the only difference between these 4 polyatomic ions. But they are all different, and so they do have their own individual names. Right, a big thing, a big important thing in chem is making sure that if something is not the same, it has a different name. Let's look at some practice problems. Here for you, I've got a bunch of practice problems. Each one of these things has a polyatomic ion in them. So I'm going to give you about a minute and a half. Again, please feel free to pause the video to take more time. Take about a minute and a half, work on these, and we'll look at answers when we come back. when we look at these practice problems here, our correct names look a little something like this. Each one contains a polyatomic ion. Most polyatomic ions are negative, which means you're going to find them in the back of the compound. There are a few that are positive, right? Ammonium being one of them. And it is totally possible for there to be a positive polyatomic ion combined with a negative polyatomic ion. Remember that Roman numerals are only necessary if your positive ion could be multiple different things. For something like calcium that can only ever be +2, you don't need a Roman numeral for it, because if I say calcium chlorate, I know that this must be +2. There's no other option for it. In our next video, when we come back together, we will look at going backwards, taking a name and reverse engineering the crisscross method to go from the name to the chemical formula, instead of what we've been doing this whole time, which is taking the formula and going to the name. But for now, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.